So far in this series of talks, we've discussed how the vibrating strings can cause an instrument body to vibrate, and we've talked about how we can characterize that vibration of the body. We've talked in terms of vibration modes and mode shapes and resonant frequencies, and we've also talked in terms of frequency response functions and how we might do a measurement on the bridge of an instrument to characterize that vibration. But there's an ingredient we haven't touched yet, and that's the subject of this talk. It's all very well to make the instrument body vibrate, but what we actually want is to radiate sound waves into the air. So we're going to think a bit about the radiation of sound by a vibrating object. Now, this is a complicated subject. And the main reason it's complicated is because there are 3 different length scales involved in the problem, and different combinations of those can make quite a wide variety of behaviour. So we've got our source of sound, like this violin over here. At some particular frequency, that then generates a sound wave which propagates through space, and after a while it reaches a listener, and I've drawn a listener right over here out in the audience, but of course the listener might also be the violinist, in which case the ears of the listener are very close to the instrument. So at a given frequency, the sound wave has a certain wavelength, which varies with frequency. Remember, we've seen those numbers earlier. That's about to be very important. Once we've decided that wavelength at a given frequency, then there are 2 things that are important. We can say, how big is the instrument body in terms of wavelengths? So how many wavelengths, or fraction of a wavelength, can we fit into the size of the instrument body? And how many wavelengths away is the listener? That might be many, or if it's the violinist, it might be not very many at all. Now, different combinations of those 2 numbers, wavelengths, how many wavelengths to the listener, how many wavelengths in the size of the violin, generate different regimes of sound radiation. Think about the listener first. How far away is the listener? If the listener is many wavelengths away, so right out there in the hall, then they're in what's called the far field. And it doesn't matter what the source of sound is, a violin or a loudspeaker or anything else. Once you're in the far field, then the sound waves are simply spreading out, getting gradually weaker according to the inverse square law. So if the listener moves a bit further away, the sound will get somewhat quieter. Different in a hall, of course. We're not thinking here about reflections from the walls. But that's relatively simple. If the listener, on the other hand, is close to the sound source in terms of wavelengths, then they're in what's called the near field. And there they may hear things which are quite different from our listener in the far field. So the violinist in particular has their ears very close to the body of the violin. At nearly all frequencies, both of their ears are in the near field, and the player will therefore hear sounds from the instrument which can only be heard locally. They don't generate sound waves that radiate to a distance. So the sound to the player really is potentially quite different from the sound out there in the hall because of this near field, far field distinction. What about the other number? How big is the instrument in terms of wavelengths? That's the thing I'm mostly going to talk about in this talk here. If the instrument is small compared to a wavelength, in other words, the wavelength is big compared to the instrument, in other words, if the frequency is low, right, low frequencies, long wavelengths, then it doesn't matter what your vibrating object is, it won't be a very efficient radiator of sound. It's simply not possible to make a lot of sound with a very small radiating object. Because you're therefore struggling to make something loud enough to work, then the design details matter a great deal, and that's the main thing that I'll be talking about in this particular talk. Once the frequency goes up, the wavelength gets shorter, and we fit many wavelengths into the size of the instrument. Then the detailed pattern of the sound waves gets more complicated, but the general efficiency of sound radiation on the whole gets better. So pretty much any vibrating structure can radiate a reasonable amount of sound once it gets up to high frequencies, short wavelengths. So it's less of an issue, although we will see later on that the details of how the sound is radiated get more complicated. But we're going to think about that first case. Very low frequency, very long wavelength. This is a really important issue from the point of view of design of an instrument body or a loudspeaker or anything else. Luckily, in that particular case, the mathematics underlying sound radiation is rather simple. Now, I'm not going to show you the mathematics as in earlier talks, you just have to believe me. But now, let me remind you of this. Here are two particular sound fields that we saw earlier, and these are both highly idealized. This one is the sound field caused by a sphere pulsating in size, staying spherical. It's called a monopole source. This one is the result if you get two of those pulsating spheres, you sit them very close to each other, but you have one sucking while the other is blowing. They're going in opposite directions. That creates this effect called a dipole field, and it has some spatial variation. There's no sound at all on this midline here where the line is white. But you can also see the colours throughout are less bright than they are in the left-hand plot. So dipole fields are inefficient. And that's no surprise, because we've had one vibrating sphere and then we've done our level best to cancel it out by putting another one right next door to it going in the opposite phase, and to a large extent it succeeds in cancelling it out. Now, these seem very idealized, especially this dipole field. When do you ever see two pulsating spheres next to each other? Well, there's another way to make a dipole source which is much more physically plausible and common. Instead of taking a sphere and pulsating it, or having another sphere next to it, we simply take our sphere or any other rigid object and we shake it from side to side. Now, if you think about it, when the sphere is moving upwards in this diagram, it's pushing the air in front of it and it's pulling at the air behind it. Then you reverse the other way and it pushes at one side and pulls at this side. So moving our sphere is a bit like having a positive source on the front face and a negative source on the back face. And sure enough, if we take a sphere and we just vibrate it from side to side, that generates exactly the same dipole field that we saw in the previous slide from the two spheres. Well, rigid objects being vibrated, they're really rather common. So these two ideas, the monopole field and the dipole field, and dipole fields we generate by this kind of mechanism you see here, that's really important. So if we have a small sound source, remember we're dealing with this case at very low frequency, very long wavelength, much bigger than the violin. And all we have to ask ourselves is, in the course of whatever that vibration pattern is, does the net volume change? If the net volume is fluctuating, then the sound field, once you get out in the far field, will be essentially exactly the same as this pulsating sphere case. So if there is volume change, you get this monopole radiation, which is relatively efficient. If the volume is not changing, then various things that could happen, usually what happens is that you get one of these dipole fields, because we've just seen that's the field that you get from vibrating an object from side to side with no change in volume. So what we can do is we can look at the low frequency vibration modes of our violin body, for example, and low frequency means we're down in the range of those signature modes that we saw in earlier talks. And we look at each mode and say, is there net change of volume or is there not? And that'll be the thing that determines how efficient the sound radiator is. But violins and musical instruments are not the only thing for which that is true. Any small sound source will be more efficient if its volume is changing. And I'm going to show a couple of non-musical instrument examples of that before we get back to instruments. And the first one is something I wonder if you've ever thought about this. If you have flowing water, does it make a noise? Sometimes, yes, it certainly does. You think about it, flowing water only makes a noise that you can hear at a distance if it has bubbles in it. And that's because bubbles inside the water, they're spheres. A bubble has a kind of bouncing resonance which is just exactly like our pulsating sphere. And it's that resonance of a bubble which makes a monopole sound source and makes noise. So you can have a little trickle of water like this left-hand picture, and as soon as it starts to generate a few bubbles, it'll make a noise, that characteristic chuckling sound of the burbling brook. Here's the seaside. Now we have waves out in the open sea, but they're not making any noise. If you're out there in a boat and the waves are passing you by, they do it in silence. But as soon as the waves reach the breach and then they break, the breaking wave, all this white here, is because it's making lots and lots of bubbles. And of course that gives you the thunderous roar of surf on the beach. Even raindrops falling in a puddle, that characteristic plop plop noise, even that is caused by bubbles. You need slow motion photography to demonstrate this, but it turns out that if you look at a water drop falling into still water, it does various things, but it makes a bubble, which eventually rises to the surface and pops again. But while that bubble is there, it vibrates a bit, and that is the plop noise that you hear when rain falls into water. So, volume change is associated with any time that flowing water makes sound. Here's another example to do with loudspeakers. Why do loudspeakers have to be put in boxes? Well, here's a schematic of a loudspeaker. It's basically just a piece of cardboard, a sort of conical shape, being vibrated backwards and forwards by some kind of electromagnetic thing here. Well, it's a rigid body being vibrated. What sort of sound field does it make? It makes a dipole field. There is no volume change. And so just a loudspeaker out on the bench, as it were, is not a good way of radiating sound at low frequencies. It's all right at high frequencies, but at low frequencies, it doesn't work. So what do you have to do? Well, the simplest thing is just to put it in a box. And all the box has to do is be there. You don't want the box to vibrate. So we've got the same loudspeaker here, but with a rigid enclosure around it. Now, as the loudspeaker cone vibrates in and out, the combined volume of the box plus the loudspeaker is fluctuating. So now it's a monopole source. And provided the whole thing is small, the whole box construction is small compared with the wavelength, in other words, at very low frequencies, your loudspeaker will make a lot more sound. In other words, its bass response will be better by being in a box. So now, finally, a musical instrument example. And this business of promoting volume change is at least one of the reasons why it's a good idea to have a soundpost in your violin. Now here's a sort of cross-section through a violin, but it's got no post and no bass bar. Now you all know that violins have stuff inside them. Most people don't know that. And most people are surprised when you point out that it has a soundpost and bass bar inside. Well, if a violin was as symmetrical as it looks from the outside, then schematically you might expect it to vibrate a bit like this sketch here in the top diagram. The vibrating string is applying a transverse force on the top of the bridge at the string notch of whichever string you're thinking about. So it's trying to vibrate the bridge in this plane. The bridge tends to rock, so one foot will push down while the other one is going up. And if the top of the instrument and the whole box was symmetrical, it would tend to vibrate in a symmetrical way like this, going up on one side, down on the other side, and then reversing, and in a way where the volumes of these two things would cancel out. So without a soundpost or a bass bar, the violin would tend to vibrate in a way with no volume change, and therefore not good sound radiation at low frequencies, long wavelengths. You put the post in, and to some extent the bar, anything that breaks this symmetry, but especially the post, and the simplest view of what the post does, it's all more complicated than this, but roughly speaking, the post tends to generate a nodal point at that position, roughly underneath 1 foot of the bridge, of course. And then, corresponding to my red line in the top sketch, we get something which still goes up on one side and down on the other, but the post has shifted it so that it's no longer symmetrical. The bulge going upwards displaces more volume in the air than the bulge going downwards. There's now a net change of volume, and straight away the sound radiation will be stronger at low frequencies. It'll have better bass response. This is the thing you can demonstrate if you're feeling brave. Slacken all the strings except the G string. Have a violinist just play scales up and down in the first position. Come over their shoulder with your soundpost setter and knock the post out while they're playing, and just listen to the change and sound from post to no post at the very lowest frequencies where the wavelength is longest, and you will immediately get that thin, tinny sound that you probably associate with school violins or with small size child violins, precisely because they're too small compared with the wavelength. So, back to this issue of near fields and far fields. Out in the far field, once you're a long way away from the sound source, what I said earlier on was that the sound field in any particular direction from the instrument simply decays away with distance by the inverse square law. But it doesn't necessarily have the same loudness in all directions. The violin, or whatever the sound source is, will have a directional pattern. Now that's what this radiation, this animation here is showing. This is a measurement of a real violin at a very low frequency, actually at the frequency of that air resonance that we talked about in an earlier lecture. It's very low. The air resonance does indeed generate volume fluctuation. I've just told you that ought to mean that in the far field it behaves like a monopole, and that's what you see. This directional pattern, I'll explain the colour code in a second, is more or less spherical. The violin body is radiating essentially equally in all directions. So this is a measurement courtesy of George Bissinger at lots of microphones, making a sphere around the instrument. The instrument is oriented with its neck vertical and downwards. The green colour is the front of the violin, the red colour is the back of the violin, but it doesn't make much difference to this one. We go to a somewhat higher frequency, 980 Hertz. Now we're beginning to get out of this range where the wavelength of sound is now getting short enough that the violin is no longer really small compared with the wavelength. The radiation pattern is getting more complicated. And what you see here is that the green blob is bigger than the red blob. There's more sound coming out of the front than out of the back. And also the pattern's a bit spiky. It's beginning to have directional characteristics. It's no longer a sphere. The final thing I'm going to show you in this talk is the same data, the same violin, but instead of taking a single frequency and rotating it so you can see it, here we're going to choose one fixed angle of view, and what's varying in the animation is the frequency. So you're going to see the radiation pattern of a violin evolving with frequency. And rather unpleasant it is too. So here we are at low frequencies, mostly spherical. Something happened there, we went through a dipole stage. But now, underneath all this heaving and twitching, the shapes are getting progressively more complicated. That's because the frequency is going up, the wavelength is going down, and the radiation pattern of the instrument is being influenced by those interference patterns that we talked about earlier. Different parts of the violin are vibrating in different directions and in different phases, and those combine to produce rather complicated patterns. We've ended up at 2 kilohertz here, and by now the radiation pattern has got lobes in it. There are certain directions where it radiates rather strongly and other directions where it's much less strong. So, and this spatial variation is probably a lot to do with the sound quality of a live violin. And it's probably one reason why a recorded violin may sound pretty good, but never sounds the same as a live violin. You can always tell if there's a live violinist in the room compared with a hi-fi system, however good the hi-fi system. So let's sum up the points from this talk. Sound radiation is complicated. I've told you some of the relatively simple things about it, but it is complicated. Everything depends on two numbers: the size of the instrument in terms of wavelength and the distance to the listener in terms of wavelengths. At low frequency, where the wavelength is very long, so the violin or the cello or whatever is, relatively speaking, rather small, you always struggle to get good sound radiation. So it matters to think about what's the least bad thing we can do. How can we get fairly good sound radiation at low frequencies? And the key thing there is that you need vibration in a way where the net volume is changing so that it's a monopole source. If the volume is not changing, you get this relatively weak dipole source. As you go to higher frequencies, so the instrument is not small compared with the wavelength, then the sound gets louder in general. The net amount of sound coming out of the instrument is always fairly good, but it becomes directional. And the directional pattern changes with frequency, and that's what you saw in that last animation. And probably, as I said, that plays a role in the sound quality of a live violin compared with a recorded one. And that's it for this talk.